Hi everyone, my name is Ankur Gupta and I'm presenting the work on in the sessions of electrokinetic flows. And the title of this talk is Thick Double Layers from Energy Storage to Diffusiophoresis. So this talk will consist of two parts. The first part will focus on energy storage. And the second part will focus on diffusiophoresis. And in both the problems, we'll see the importance of thick double layers. So before I jump into the details, I thought given the online nature of this meeting, it'll be a good idea to share the take-home messages with you about from this talk. So like I said, there are two parts of this talk. One is energy storage and one is diffusiophoresis. So in energy storage, what we did was we studied the problem of a charging dynamics of electrical double layers in a cylindrical nanopore. So there is a cylindrical nanopore you see here with radius A and length L pore. And what we wanted to see was when we charge the system by applying a potential psi d, what's the charging dynamics when the systems have thick double layers relative to the pore radius. So if you have thick double layers, the double layers will basically go throughout the region of the pore. So this problem has been solved for thin double layers. And in that problem, the basically solution reduces to an effective circuit model where you have a series of resistors and capacitors. So we solved the same problem, but for thick double layers. And what we found was remarkably that the effective circuit model remains identical. However, the meaning of the capacitance and resistance changes. So for instance, the capacitance becomes volumetric for thick double layers as compared to surface areal, which kind of makes sense because when they're thick double layers, they're going throughout the volume of the pore. So the capacitance becomes volumetric. And when they're thin double layers, they're only around the surface. So it becomes surface areal. Similarly, this potential psi d is actually reduced when you have thick double layers because you don't have enough region for the thin double layers to actually develop completely. So even though you think you're applying a potential psi d, you're actually applying a less potential, and so the applied potential is reduced. There are some other details about resistances, but at the end of the day, the most important quantity, which is the charging time scale, actually also changes. And in the thin double layers scenario, it's actually proportional to the Debye length, but in the thick double layer scenario, it becomes independent to the Debye length. It actually reduces to the diffusive time scale of an ion. So this will be basically a take-home message of the first part. And I hope that if you're interested, you will actually stay on and listen to the remainder of this talk. So now let me just share with you the details of the diffusiophoresis part. So in this problem, what we did was we studied the various parameters affecting the mobility, diffusiophoretic mobility. If you're not familiar with diffusiophoresis, it is basically a phenomena where a colloidal particle moves in the presence of a concentration gradient of a solute. We are here focused on the concentration gradient of an electrolyte. And whenever you have an electrolyte and a charged surface, like a colloidal particle, there will be a double layer. So what we basically wanted to study specifically was what is the dependence of the diffusiophoretic mobility, denoted here as DDP, on the concentration gradient of the electrolyte CS. And what we found was that, so you can basically focus on this plot on the main blue line here, which is the blue solid line, which has a maxima, is that there is a maxima for diffusiophoretic mobility from around 1 to 10 millimolar salt concentration. Below that region, and this is basically for a colloidal particle about a micron in size, this trend that I'm describing. So below that, basically concentration, the finite double layer thickness effects start to come in, and the diffusiophoretic mobility actually reduces significantly. Whereas for larger concentrations, there is charge screening, which basically reduces the diffusiophoretic mobility. So there is a sweet spot where you will see maximum diffusiophoretic mobility. And this, again, I said the result is here for a 1 micrometer particle. So we actually experimentally also validated this trend where we showed that there is a maxima in diffusiophoretic mobility. So this will be the essentially the conclusion of the diffusiophoretic mobility part. So I'll now first go on to the energy storage, and then I'll move on to diffusiophoresis. And I hope that you will stay on and actually listen to both the topics. For energy storage, let me start by uh, first just describing you in broadly what is the importance of electrolyte transport. So even before I jump into the details, so electrolyte transport is actually important in energy storage, like I said. So it is used in supercapacitors, batteries, In the 2019 report in Guardian actually termed the current age as an ion age because the energy storage devices will be dependent on ion transport. Electrolyte transports are very relevant for energy storage. They're also important for desalination. It is possible that you can apply such a large voltage that you can actually remove salt from water, and that is known as capacitive deionization. And that's actually also an important application of electrolyte transport. It also has implications in biophysics. So for instance, there was a very recently a nice perspective in PNAS about colloidal stability of a living cell, how we can think of proteins and as colloids, and electrolytes surrounding that proteins would actually end up creating an electrostatic repulsion force between proteins, and how that acts as stabilizing mechanism for protein. So it also has implications in biophysics. And finally, it's used very widely in analytical tools. For instance, gel electrophoresis, you utilize electrolyte transport principles, electrophoresis, and so on. So basically, electrolyte transport kind of goes around in all of these different concepts. And what we will be focusing on today would be the topic of energy storage and diffusiophoresis, which I would say would come around this analytical tools idea, kind of like a counterpart of electrophoresis. Like I mentioned before, the talk will be divided into two parts. So let me first start with supercapacitors. So if you're not familiar with supercapacitors, they're actually energy storage devices, much like batteries, where you have two porous electrodes in the end and you have an electrolyte in the middle. If you compare them to batteries, this is a good plot to look at specific power versus specific energy, where you can see that batteries have more specific energy but lower specific power, whereas supercapacitors have lower specific energy but higher specific power. So supercapacitors are actually useful in high power applications like load leveling, in initial acceleration, or energy recovery in electrical vehicles, in emergency exits of aeroplanes, and other applications. So wherever you need high power or a burst of energy in a short span of time, supercapacitors are important. And recent research in this area has actually focused a lot on the material design of these electrodes, how to control the pore sizes. And you can see here for in this plot, maybe it's not visible very clearly, but the pore sizes are going in sub-nanometer region, 2 nanometers, 3 nanometers, sub-nanometer regions. And there is also a great interest in, understanding how ions will actually layer near within these electrodes, porous material, whether there will be layering of ions and how that layering would change the energy storage properties. So what we were interested in was understanding that there is a lot of interest in this pore size distribution. However, the limit which is widely available is for large pore sizes or thin double layer limit. So here thin double layer limit means ratio of the Debye length to the pore size. And if that limit is small, it's the thin double layer limit. And that will typically occur for macro pores like in microns or hundreds of microns. But as we see here in the plot, that the research has increasingly focused on nanopores. So it was our interest to understand what will happen when we have thick double layers. So basically the double layer is comparable to the pore size. So let me first quickly, briefly show you the result. It's a very classical result for thin double layers in a cylindrical nanopore, and then talk about how we can extend that to a thick double layer. So in thin double layers, what you can imagine is, you can imagine a pore, again a pore with radius A, and then there is the surface, there is a thin double layer. So this lambda is a Debye length, which is a measure of the region which is charged near the surface. And if this lambda by A is much smaller than 1, we call it a thin double layer. And what essentially is the physical mechanism is that the current is basically coming when the charge is changing in this double layer, and it's being carried by this bulk region, which is electroneutral. So it basically, the electroneutral bulk becomes a resistance, and the charge being stored in the region becomes a capacitor. So this is basically this effective circuit model, that you have a series of resistors and capacitors, and that's how you describe this model. And this is well known and very commonly used in literature. And what we wanted to basically understand was whether, so the governing equation for the system essentially looks like an unsteady diffusion equation. So tau is dimensionless time, z is dimensionless length in the z direction, and these are just boundary conditions. And this is an unsteady diffusion equation, which has an analytical solution. So we can solve for the system And the time scale here is given by this sort of factor where you have a length square by d, which is the diffusion time scale multiplied by this ratio lambda by a. So it's proportional to the Debye length. That's essentially uh, the time scale that comes out from this analysis. And this works really well. This has been experimentally validated. But as we said before, in supercapacitors, really the lambda is very close to a, and the lambda by a is actually not very small. So what will happen to this limit when you are actually going closer to 1? And that is something we were interested in exploring. So to do that, what we did was we essentially went back to the same problem. So it's exactly the same problem where we have a length L pore, L pore. LSDL is the region of the outside the pore, which you can basically vary as a parameter. Uh, uh, and then you have a bulk region where potential is 0 and electrolyte is electroneutral. At t equal to 0, you apply a potential such that the electrical double layers start to develop. And we wanted to understand what will happen for any Debye length, not necessarily for thin double layer, for any Debye length. So what we did was we actually solved the Poisson-Nernst-Planck equations. If you're not familiar with them, basically they are transport equations for ions, C plus and C minus. And what the form you see here is actually written in charge and salt. So charge is C plus minus C minus, and salt is C plus plus C minus. And this is for a 1:1 electrolyte, which means like NaCl, KCl, and so on. These are the standard equations that come out. And this is the Gauss's law, which essentially is trying to say that the gradient of electric field, or which is the Laplacian of potential, is equal to the charge stored in the system. So these are standard equations. What we did was we solved them numerically using a direct numerical solution solver. And what we found was that if we look at the potential profiles that come out from direct numerical simulations, let's say we are walking along z equal to 0, right? We're walking along z equal to 0, and we are looking at factor a by lambda. So a by lambda, if a by lambda is small, that means we are thick double layer limits because lambda is big. And if a by lambda is big, we are in thin double layer regime. So what you can see clearly is that when your a by lambda is small, there's a sharp jump at the potential at z equal to 0, which is at the pore mouth. And whereas if you look at the surface, just let's say we are walking along the surface here, very close to the wall, jump happens for all the Debye length. It doesn't matter if you're thin or thick. So this was very instructive and important for us, is that there's a jump happens everywhere when the Debye length is thick, or when we have a thick double layer regime. And therefore, what we basically decided was that we will try to now create an analytical model to predict this behavior, which comes out of direct numerical simulation. And the reason there is a jump is because Debye length is because the double layer is everywhere. So there is we can expect there will be a jump. So what we did was that we constructed a model. I will not go into the details, but what are the challenges of constructing a model here is there is no electroneutral bulk, right? And there's a rapid change in the potential at the mouth of the pore. So to actually construct the model, what we did was we assumed that the salt concentration remains constant. And this can only happen for small potentials. So our model is actually valid only for small potentials, or the linear limit, if you're familiar with this terminology. And then what we did was we treated this sort of jump, which happens at the surface, akin to a jump boundary condition. So what we did was we equated currents between three regions: the region outside, the region inside, and the thin region in the middle, which is like a jump boundary condition. And finally, we assumed the aspect ratio is small, which is typically true in experiments too. So by doing all of that, we were actually able to construct a model in the system. And like I had mentioned before, it actually comes out to be identical. This is an exactly the same effective circuit that you get out. There is a capacitance coming out from the system. There's a resistance, there's an applied potential. However, as I mentioned before, the meaning of these elements change. So let's look at the meaning a little bit more carefully. So the capacitance becomes volumetric. So the capacitance you see is capacitance per unit length. So here you have dependence on 2 pi a, which is again the radius. So 2 pi a times because it's per unit length. So this is surface area per unit length. Whereas you have pi a square here, which is volume per unit length. So basically for thick double layers, the capacitance becomes volumetric. Similarly, the applied potential is same as the applied potential for thin double layer limit, but for thick double layer limit, it actually reduces significantly. And finally, for time scale actually becomes the long time scale here, which is independent of Debye length. whereas for thin double layer limit, it was actually equal, it was actually proportional to the Debye length. And what I have done here is shown you the results of the analytical model, but we can actually also compare it to the direct numerical simulation. So what you see here are a lot of plots. So let me walk you through. This is the potential at the center line at z equal to 0. And the solid lines are results from direct numerical simulation for different times. The dotted lines are the thin double layer limit extension. So if you extrapolate it, which is what is commonly done in literature, which basically shows you that you get completely wrong results. And the dashed dot lines are the overlap double layer limit, which is our solution. And you can see we get a near perfect match. Similarly, we can actually predict the charge stored within the whole region at the center. And you can see we can get almost a near perfect match with direct numerical simulations using our model. We can also calculate the charge profile radially. So this is the radial direction. And you can see we are able to get perfect match with direct numerical simulation. So in summary, essentially we created this model which is able to explain the charging dynamics of a thick double layer regime, where the effective circuit model comes out to be identical to thin double layer limits, but the meaning of the resistors and capacitors is different, and the time scale is also different. Now I will move on to the second part of the talk, which is diffusiophoresis. And what I will do is I will talk about the effects of different parameters on diffusiophoretic mobility. So if you're not familiar with diffusiophoresis, like I mentioned, you can apply a salt gradient here, electrolyte gradient, and all the particles will move in that direction. So this is known as an external concentration gradient. And as you can see here, these fluorescent particles are moving all in the horizontal direction because that is the direction of the concentration gradient of electrolytes. The particles actually move up the gradient or down the gradient depending on the properties of the electrolyte and the particle. There's also another kind of diffusiophoresis, which is self-generated concentration difference. So it's more local in that way, and the concentration gradients are more local. So you can actually see very nice behavior like crystallizations of particles, self-propelled particles. They can combine, they can make these beautiful structures out of them. What we are focused today on is the external concentration gradient idea, where we have the common concentration gradient being applied to all particles. Just to quite quickly explain to you how this process works, let me do an order of magnitude analysis. And what I will do is I will do the reverse problem where the particle is stationary and the fluid is moving, which is known as diffusiosmosis, but the diffusiophoretic is basically identical in terms of scaling analysis. So if you do an order of magnitude analysis, let's assume that we have a concentration gradient in the x direction. The surface is stationary with a given charge density q, and because the concentration gradient is changing, the diffuse layer, which is dependent on the thickness Debye length, is dependent on the concentration gradient of the electrolyte. It is also changing. And what essentially diffusiophoresis means is you're balancing the shear stress in the because of the velocity gradient in the y direction with the pressure gradient, which is because of the change in concentration gradient of the solute. So the pressure gradient is simply kBT dc by dx, which kind of makes sense because kBT c is the pressure. Simply we can say that the gradient would be mu vdp by lambda square, where lambda square is the Debye length. Again, this is a length scale of the diffuse layer thickness, which is itself dependent on Cs. So the velocity scale is simply when you balance these two stresses, you can actually get an order of magnitude estimate for the velocity of diffusiophoretic velocity. Now here lambda has not been substituted in terms of Cs. And if you do that, which is again a very common formula, what you get is a very close result to the exact result. What you get is a logarithmic dependence on concentration gradient of the solute of the diffusiophoretic velocity. The exact result actually has a correction factor, it's very similar, but there is a function u naught of zeta. And a lot of publications that we see in literature in this area actually kind of describe this whole expression, which is to the left of this logarithmic dependence, as diffusiophoretic mobility, and they assume that to be constant. However, that was kind of a bit surprising to us, is because if it's a logarithmic dependence and it's a gradient, it would mean that if the concentration gradient happens from 1 micromolar to 10 micromolar or 1 molar to 10 molar, the velocity should be identical because it's logarithmic. So it should not depend on the units. It can be micromolar or molar or millimolar. Everything should be the same. However, the implicit assumption is that the diffusiophoretic mobility is constant, that it does not depend on the salt concentration. So that is what we wanted to challenge, is that there is a dependence on diffusiophoretic mobility. And to do that, what we did was we accounted for two effects. Uh, so one of the effects is actually the finite ion size effect, finite double layer thickness effect, in the sense, because you have a double layer thickness, the lambda by A is assumed to be typically much smaller than 1. But when you have very small concentrations of the electrolyte, that value will start to go towards 1, and thus finite double layer thickness effects become important. And actually, we are not the first ones to do this. This was done way back in 1984, and basically we used the result given by Privy et al. And substituted the result for U1, which is a correction factor for the finite double layer thickness effects. And just to give you an idea, the top portion, which is the leading order solution, is linear in zeta, which is the zeta potential, but the correction is actually exponential in zeta. So this starts to dominate a lot when you have lambda by A close to 1, and that is something what we basically calculated for different systems. The other effect we did was, and lambda here is a function of CS, like you mentioned, so it is actually evolving with space and time. And the other thing that we did in this problem was actually think about the surface charge condition, that the particles can be constant potential, constant charge, and if they're constant charge, their zeta potential will also depend on concentration. So their zeta can also depend on concentration of the solute. So this is what the results look like. So first, let's focus on the dotted lines, which are black lines and solid line. So this is the most common assumption, that you assume diffusiophoretic mobility is constant. This is commonly used in literature, or people sometimes use constant charge conditions, which show this line that the diffusiophoretic mobility is really high for dilute systems and decreases monotonically for large concentrations. And that happens because constant charge systems means when you have a small concentration, your zeta potential increases or your velocity increases. What we argued was that the reality is somewhere between the two solid lines, the constant potential system, where you have a decrease because of finite double layer thickness, and the constant charge system, where you have a decrease because of finite double layer thickness and charge screening at large concentrations. So finite double layer thickness becomes important in small concentration, and charge screening becomes important at large concentrations. And the reality, we believe, is somewhere in the middle of these two lines. So this is what we predicted. So we predict that there's a maxima in diffusiophoretic mobility. These results are specifically for NaCl solution with 1 micrometer polystyrene particles. Of course, these results would change for different electrolytes, different particle sizes, but the rough trend should remain the same, that there is a maxima. So we cannot expect these, we cannot expect transport rates from diffusiophoresis to really explode. They have to be limited by this fact that there is a maxima, and as soon as you start to go into the extremes, you will die down and the diffusiophoresis will no longer be dominant. And we actually experimentally validated this. So what we did was we kept the logarithmic concentration gradient same. So what you see here is a dead end pore. So we fill these pores with particles, and there is a concentration gradient reservoir outside the pore, and then a concentration inside the pore. And let's say the concentration outside the pore is 1, then the concentration inside the pore is 10. So the ratio was always 10. So if it is 0.1 outside, inside it is 1. If it is 1 outside, inside it is 10, 10, 100, 100,000, and 10,000, 10,000. And all these concentrations are in millimolars. So we did this, and in this case, the particles move toward higher concentration, so they get compacted. And you can see the compaction, which is representative of the diffusiophoretic mobility, is maximum in the middle and decreases on the two sides. Of course, there are a lot of factors which are going on in the system which we have not accounted for. For instance, there is diffusive osmosis from the walls. There is sometimes 3D effects and 2D effects that come in, which we are not incorporating in our 1D model. But you can see that our model actually works pretty well and is able to capture this maxima into the system. I should again emphasize that this is not an exact model, but it is able to sort of demonstrate that there is a maximum diffusiophoretic mobility, and that finite double layer thickness and charge screening effects should be taken into account while thinking about diffusiophoretic processes. So again, the take-home message is diffusiophoretic mobility has a maximum, and transport rates achievable through diffusiophoresis are limited. So just to summarize, I discussed two talks, the supercapacitors and diffusiophoresis. If you're interested in these themes, I invite you to check out our papers. Here's the paper for supercapacitor, which was published in Physical Review Letters this year. And this was a paper in Diffusiophoresis, which was published in Sort Matter this year. Just before I leave, I'm starting my independent research group titled Laboratory of Interfaces, Flow and Electrokinetics at CU Boulder in the Department of Chemical Engineering. If you're interested in these themes and if you're interested in kind of talking about these topics, I invite you to please write to me. I'm pretty prompt on emails and I'll be happy to collaborate with you and or work with you. So thanks for your attention and I look forward to receiving your questions.